You know how your phone can finish your sentences? Or how a website can translate an entire language in, like, a split second? Well, it's not magic, it's memory. Today, we're going to crack open the machine and take a look at the actual architecture that lets computers understand not just our words, but the sequence and the context behind them. Let's dive in.
So, here's the plan. We're going to go on a little journey. First, we'll nail down the absolute fundamental problem of language. Why order is just everything. Then, we'll see how we get text ready for a machine to even read it. After that, we'll meet the very first model that had a basic memory, find out about its one critical flaw, and finally, uncover the really ingenious upgrades that gave machines a powerful long-term memory.
All right, let's start at square one, the absolute core of the whole challenge. See, for a computer to really get what we're saying, it can't just know the words we use. Nope, it has to understand the order we put them in. That sequence, it's everything.
And this, right here, just illustrates the point perfectly. Look at the left side. Dog bites man. Okay, pretty standard stuff, not really news. But on the right, we've got the exact same three words. Man bites dog, just shuffled around. Man bites dog. Whoa, suddenly, that's a headline. The meaning is completely, totally different. This is the sequential puzzle that these early models had to solve.
Okay, so before a neural network can even attempt to understand a sentence, we've got another hurdle. Computers, they don't speak English, they speak math. So our first job is to translate our language into theirs. We have to turn our text into numbers.
And this is done through this kind of digital sanitation process. We're essentially cleaning up the text. We break sentences into individual words, get rid of all the extra fluff words like the or and simplify everything down to its core root. The whole goal here is to create clean, uniform data so the machine can analyze it without getting tripped up by weird grammar or capitalization. One of the very first tries at this was a method called bag of words. And it's super simple. It just counts how many times each word shows up in a sentence and throws them all into a bag, totally ignoring where they were in the first place. And you can probably already see the problem, right? A bag of words model would see dog bites man and man bites dog as the exact same thing. It completely, utterly fails our sequence test. So yeah, we needed something way smarter. Enter word embeddings. Now this was a massive leap forward. Instead of just counting words, this technique represents every single word as a point in this complex, multidimensional space. And the key idea is that words with similar meanings get placed close to each other. So dog is near puppy, and happy is near joyful. It's basically a map of meaning. And here's where it gets kind of magical. These relationships go way beyond just simple synonyms. This famous equation here, it shows that the model has actually learned abstract concepts like gender and royalty. If you take the location for king, subtract the location for man, and then add the location for woman, you land almost exactly on the spot for queen. I mean, come on, that's mathematical poetry, and it is the foundation for everything that comes next. So with our words now turned into these meaningful numbers, we can finally build a network that can read them in order. Let's move on to our first real sequence model, the recurrent neural network, or RNN for short. This was the first architecture that was actually designed with a form of memory. The genius of this architecture is its loop. For each word it reads, the network doesn't just see the word itself, it also gets what's called a hidden state, which is really just a memory of the words that came right before it. It combines that new word with this memory, spits out an output, and then, and this is the absolute key, it passes an updated memory on to the next step. This recurring loop was the first real shot at giving a network a sense of history. And this was totally revolutionary. But as powerful as the simple loop was, it had a major, crippling weakness. It was forgetful. And this created a brand new problem that we had to solve. Let me just put the question to you. Think about reading a really long paragraph. To understand that last sentence, you might need to remember some tiny detail from the very first sentence, right? So what happens when that memory needs to stretch across dozens or even hundreds of words? Well, this leads to something called the vanishing gradient problem. The best way to think about it is like a game of telephone. The information or the signal from that first word gets passed down the line, but at each step it gets a little weaker, a little more garbled. By the time you get to the end of a long sentence, that initial signal has pretty much vanished. The network literally forgets what it saw at the beginning. So the challenge was clear. We needed a much more sophisticated memory system. We needed an architecture that could actually choose what to remember and what to forget. And this is what led to the creation of two brilliant upgrades, LSTMs and GRUs. First up is the Long Short-Term Memory Network, or LSTM. It's a special kind of RNN, but if you look under the hood, its internal architecture is way more complex. Its big solution to the forgetting problem was to create two key things: a dedicated memory highway, called the cell state, and a series of gates that act like information traffic cops. Okay, let's break down this amazing architecture. The cell state is like an express conveyor belt for memory. It lets important context from the start of a sentence ride all the way to the end without fading away. But the real genius here is the gates. You've got a forget gate that learns to throw away irrelevant info. You've got an input gate that decides what new information is important enough to actually store on that conveyor belt. And then you have an output gate that decides what part of the memory is actually useful right now. These gates give the network incredibly precise control over its own memory. Now, building on the success of LSTMs, researchers developed a slightly simpler, more efficient version called the Gated Recurrent Unit, or GRU. The key idea here was all about optimization. It took the core concepts from the LSTM, but streamlined the whole architecture to make it faster and require less computing power to run. So, let's put them head to head. The LSTM is the more complex beast, right? It has 3 separate gates that are all managing that separate memory conveyor belt. The GRU is the streamlined model. It cleverly combines the forget and input gates into one update gate, and it merges its memory right into the main information flow. This just makes it simpler and faster. So while an LSTM might have an edge on some super complex tasks, a GRU often gives you almost the same performance for a lot less computational cost. It's that classic engineering trade-off between raw power and pure efficiency. So when you really step back and look at the whole timeline, from bag of words to RNNs, LSTMs, and GRUs, the entire story of these models is really just a relentless quest to build a better, more robust, and more intelligent form of memory. Each new invention was a direct answer to the problem of forgetting. And that leaves us with a final thought. We have built machines that don't just process words anymore. They actually remember the context and the flow of our ideas. So the real question isn't just how they work, it's what new, more meaningful conversations this technology is going to let us have. Thanks for exploring that with me.